computer. Okay, welcome back this afternoon. This is Chemistry 2330. First thing I'll do is I'll go through the administration stuff. You should have all gotten an email about the lab. Okay, I've broken in the lab sections so that you should get a specific lab, one for just you and your lab instructor and your group. And then you get the bulk one that has all of them in case you misplace that one. You need to remember whether you're in group A or B and go ahead and get that. But you should get a specific email every Friday as to what you should be doing. I will be sending out an email today or tomorrow. We're going to do one minor change to the system where we want you to do the pre-lab. Instead of doing it handwritten before you go to class, I want you to upload it to Canvas. So, but wait for that email. Don't do it yet. And then we'll be able to do that. So for this week, what I'd like you to do is at least take one mock exam. I have one today and one on Wednesday scheduled already. The one today starts at 2 p.m. and goes till 6. It'll take you 15 minutes, or it shouldn't even take you that long. It should take you about 5 minutes to log on and everything. Now, remember, I sent you an email about how to do testing on the Proctorio. And it's best to basically shut all your programs down, maybe restart your computer, restart your cable modem or your modem, your wireless modem, if you can. And then go ahead and only open your Google Chrome and your Proctorio and then start that. The only thing you'll need for this one is really a photo ID. It can be your student ID or your driver's license, it's fine. And again, unlike Examity, these are not live proctored. This is AI proctored, artificial intelligence. So basically anything that it shows there is going to be basically not looked at by humans unless your quiz comes up incredibly suspicious, and then I will review it for suspicious behavior. So there's that added level of comfort for those of you who are stressed. I know Examity stressed me out, so I'm sure some of you have had bad experiences with it as well. So we should have that level of stress off, and by doing this mock exam, if everything works, then you should not have a problem. You should be ready. If everything doesn't work, contact Top Hat support, and they will try to figure out, is there a setting on your computer that they can help with, and then take the one on Wednesday. If things are not working by Wednesday, then go ahead and email me. We'll figure out something. And I'll set up another mock exam for the following Monday in case anybody still has any issues. And then I will live monitor the exam so that if you're having trouble, go ahead and email me during the exam, and I can answer questions or unlock you or do stuff like that. So those are things that we can do. And so that is something I will do. I will be live during that entire thing to answer questions by email if you're having trouble. I've done this multiple times over the 4 or 5 different classes now, and we have figured out how to really overcome almost every little eventuality I've seen so far. And so we'll definitely be able to be ready and take our exams one way or another. Okay, so due this week is class today and class on Wednesday, and we're going to have an activity the second half of class on Wednesday. This is basically to give you practice with chirality and assigning chiral species. It also gives you a little bit of practice drawing, okay? And so I will email that out on Wednesday morning, and so that you have that for class to help doing on that. And it's going to be another 20, 30 minutes of doing the in-class activity, and you'll upload the results to Canvas, okay? So as you may see, the homework for chapter 7 is due tonight, but the homework for chapter 6 is not due until Friday of this week, September 25th. And so that means that you'll have all 7 sets of homework will be completely graded and be available for review before the exam, okay? And then again, we're gonna have our review on Monday, and I'll give you some strategies on how to do that. We'll have a mock exam on Monday if we still have people who are having issues. And then I'll review my top things for each chapter that we can focus on. Okay, and then for the exam, it's going to be multiple choice on Top Hat. Expect about 35 questions 30 to 35 questions spanning all 7 chapters. So, you know, 5 questions per chapter, about. Okay. Any questions about that administration before we move on to today's lecture? Got nobody in the waiting room. You may not use notes for the test. The only thing you can have for the test is a blank sheet of paper, a couple sheets of paper to write stuff on, and your computer. I have found a way to embed a periodic table of contents into each and every exam. And you'll notice that when you go and take the mock exam, there's a periodic table at the beginning and the end of the exam, so you can scroll whichever's closer to use that as your reference. So the only thing you can use for the exam is your brain, your scratch paper and a pencil, and everything else is provided electronically on the computer. Okay? All right, so let's go ahead and start chapter 6. And the reason I separate chapter 6 is it's kind of a challenging topic. And instead of doing the goals, what I'm going to do is I'm actually going to do a full, you know, lecture on every slide, and that will culminate in that activity we're going to have on Wednesday. Okay, so I'm going to go ahead and share my screen. So, turns out that there are so many details about, you know, you have to get all these details right and in order to really get this concept down, that the 3 goals, while they are posted on Top Hat, I think it is better for me to go ahead and do a full lecture on this, because it breaks it down into different types of isomers, and we have to look at a couple different things, and I think it works best live. The exam is during regular lecture time next Wednesday. Yes. Okay, so this is chapter 6, and it's chirality. Okay, chirality is a special type of 3D spatialization of organic compounds, okay? And so what I want to do is start talking about the relationships with different kinds of isomers. When we did alkenes, we said that we had stereoisomers because we had fixed, we couldn't rotate around that double bond. Those areas were fixed in space. And so when things are fixed in space, we call those stereoisomers, because it's how you look at it. So you have it. Now, within stereoisomers, there's a couple different types that we're talking about. Okay. So in general, isomers are just different compounds with the same molecular formula, and they're also known as, conformers or whatever. Now, if you have all of the exact same bonds, then you have, you can have the different isomers or related isomers there. However, if you connect all those atoms in a slightly different form, like maybe have a different functional group, these are called constitutional isomers, meaning that they have all the same atoms, but they're connected differently. So isomers takes account for all of these as long as they have the same molecular formula. Constitutional is how you put them together. Now, stereoisomers have exactly the same connectivity, except that there is going to be something about their relationship in space, okay? So, for example, with the double bond, our cis and trans and our E and Z, those are stereoisomer terms because we have a fixed location in space. However, when we have sp3 hybridized carbons, i.e. tetrahedral carbons, we have a different way of looking at this, okay? So because we're not looking at a non-rotation, we're actually looking at 4 different things bound to the same carbon. And we call those enantiomers, okay? So these are stereoisomers that have a specific orientation. Now, if you have more than one carbon with 4 different things attached to it, then you can have what we call diastereomers. And there's multiple versions of that, okay? So it's enantiomers are only 1 carbon with 4 things on it. Diastereomers are 2 or more. Okay, so that it's very important that we separate those 2 definitions. Okay. So let's go and define enantiomers. We're only talking about 1 carbon that has 4 different components. So The only way we can do this is that we have to have 4 different things bound to a carbon. And when we have these 4 different things bound to a carbon, we can make a non-superimposable mirror image. Meaning if you draw the mirror image of the compound right here, and then try to rotate them around and stack them on top of each other, they will not stack. There's always going to be 2 groups that are swapped. Okay? If you can do that, this is called an enantiomer. And that compound is what we call chiral. So let's look at this one in particular. Here. So if we look at the ball and stick structure first, it's kind of interesting, but that's why we don't draw ball and stick in class. We want to draw it with wedges and lines. Okay. So in this case, we've drawn out the structure in wedges and lines, and we see that it has a 3-dimensionality to it. Okay. So whenever we do this, whenever we have straight lines that are like the straight lines, we assume them to be in the plane of the paper that we're looking at, okay, or the screen. And then if something's popping out at us, we have a solid wedge. And then if something is going behind the page, it is a dashed wedge. Okay? So this is how we can display 3-dimensionality in 2 dimensions. So what that means is that these 3 atoms are all in the same plane. This atom is coming out of that plane toward us, and this atom is going into the plane away from it. So that's what that drawing structure means, okay? And so it gives us a very definite way of looking at these structures, and we definitely see the 3-dimensionality associated. Okay, now, if we take that compound and we drew the mirror image of it, so what I always like to do when I draw a mirror image is start with one, draw that carbon, then that carbon, then this carbon, and that one, and then making sure each of the groups are, these agree with those, and this agrees, and then this is on the way back. So you draw it from the center out, okay? So now we have what we call the mirror image of it, right? Because these both atoms are behind the plane. Both of these are in front of the plane, and we still have the same 3 atoms in the plane on both sides. Okay. We see how that's a mirror image and how these are actually the same compound drawn as an image. So once we draw them as a mirror image, if we were to then pull one of them off the screen and try to overlap with the other and try to superimpose them, then that's telling us whether or not we have a pair of enantiomers. So in this case here, if we did that, if we pulled this off the paper and put the oxygen carbon and this carbon in the same plane, rotated around, we would see that this group right here would end up going behind us and going behind the plane of the paper. And the hydrogen would come, so if we rotated around 180 degrees, the hydrogen would be forward. So that means the hydrogen would overlap with these, and the methyl group would overlap with these. That makes them non-superimposable. Okay. So let's look at that again. Okay. So now that we draw our image here, what I want to do is, in your mind, go ahead and rotate that 180 degrees. So we're taking this methyl group and rotating it all the way around to this side so that it matches this. So that methyl group is going to be in the same configuration as this one right here. And if we do that, what we see is that this ethyl group is now behind the plane of the paper because of the dash, and the hydrogen is in front of the plane of the paper because of the solid dash. Okay? Now, that means that those 2 groups are not going to be able to overlap. They are not the same group, therefore they are different compounds. And that means that the original molecule plus the mirror image, that pair of molecules is now a non-superimposable pair, which makes them a pair of enantiomers. Okay? So let's look a little deeper into how to see these things, okay? Okay. So let's look at it again right here. And this again is our original molecule here. And now we have them drawn in the same orientation such that these three atoms are still in that same place and these three atoms are all lined up. But we see that in the original molecule here, this ethyl group is sticking out at us. And in this one, it's green. So that makes it not the same place in space. Okay? All right, so it has literally swapped locations in space. And when they do that, that makes it different. Okay? And because they're different molecules, they have different properties. And so this pair is what we're going to have to figure out as to how they are different and how we would name them. Okay, so okay, let's start right where it was. All right, so enantiomers by definition are stereoisomers. One of them is what we call chiral. Chiral refers to a relationship between pairs of objects. In fact, they show handedness. Okay, so if you look at your right hand and your left hand, they are non-superimposable mirror images of each other. You would put a mirror in front of this, the thumbs would line up, the index fingers would line up, then the ring fingers would line up. And so they are mirror images of each other. But when we try to lay them over the top of each other, we have a mismatch. Thumbs are lining up with fingers and fingers are lining up with thumbs. So that's the way to look at what we think is chiral, things that are mirror images but cannot overlap. So this only happens in organic chemistry when we have 4 different groups bonded to the same. Now, the carbon those 4 different groups are bonded to is what we call the Stereoisomer. Basically, that's the one carbon that controls the spatialness, where those things are in space, and therefore that's what we get from the stereo portion of it, and the Stereoisomer. So sometimes it's called chiral carbon, stereocenter. Those are all the same thing for which carbon is controlling stereochemistry. Now, there are things that are called achiral or not chiral. Okay, a not chiral compound is something that can make a mirror image of it and superimpose. What will happen a lot during exercises and homework is you'll see, oh, is this molecule chiral or non-chiral? The first thing you need to do is look to see if there are all 4 groups are different. So if we look at this particular example here, you see hydroxide is different than hydrogen, different than methyl group. Ah, we have another methyl group. That means we have 2 methyl groups. That means that when we make their mirror image, we can line it up so those 2 methyl groups match where they go. And so if you have 2 of the same groups, then you do not have a stereocenter, and it becomes achiral without chiral. So the first thing we look for when we're looking at chiral objects is 4 different groups attached to the same carbon. And so there's also another way to look at this is that if you have the mirror image, so there's a lot of feedback there's a lot of people having feedback issues right there. I am in my same quiet room, so, okay. See, let me move that. All right, has it cleared up yet? I might have accidentally covered the microphone. Okay, let me turn my microphone up. All right, so we're better, right? Okay, great. All right, thank you very much. You can also go back and review the video because that should have the clean sound. No, it'll have bad sound too. Ooh, okay. All right, so well, we fix it. So when we do that rotation, those methyl groups will line up, and that makes them non-chiral. Okay. So, but the first thing to look for is 4 different things. Okay, so to summarize what we've learned so far, an object that is non-superimposable mirror image is chiral. Non-superimposable. Most common cause of chirality is having 4 different groups bonded to the same carbon. When we have 4 different groups bonded to the same carbon, we call that the stereocenter or chiral carbon. If an object can be superimposed with this mirror image, it's not chiral. All right. So now if you can draw a mirror image and it is not superimposable, one of those is one part of the pair of enantiomers. The other one is the other part of the pair. And just like hands, or well, gloves, the enantiomers always come in pairs. Okay. So if you have an enantiomer, you're going to have 2 molecules. That's not true for diastereomers, so that's very clear. Enantiomers always come in pairs. Okay, so the best way to draw chiral compounds is to draw them, I think, when you're first starting out, to draw them in this configuration here, okay? Now, the reason I say that is that it makes it easy to rotate these things along this axis. So imagine setting it on a table and being able to just rotate it in your mind, okay? However, there are several other techniques for learning this, and if this technique does not work for you, you cannot spatially see this, go to Organic Chemistry Tutor on YouTube, and he has 2 other methods for this that work pretty well for some people. But this is what I use, and I also have one that I call the Pinwheel Method. And if you're having trouble, go ahead and email me. We'll set up a Zoom meeting and I'll show you the Pinwheel Method. Okay, so the best way that I have to do is to draw it in this configuration with wedges, because then when you put your mirror here and you make your mirror image, it makes it easier to see. A lot of times this right here looks like it's pretty easy to do, but sometimes you forget that there's a hydrogen there. So in this case here, if you can draw that and look for that hydrogen, that works as well. Okay. So one of the things I like to always do is to get one of those prominent groups, something that's different than all the others, and make that the axis that I turn on. Okay. So on this, what we can do is, using that stick figure, as long as we remember that there is a hydrogen back here, and we want to draw the mirror image of it, here's one way we can do that, okay? So in this case right here, what we're gonna do is we're going to put our mirror right here and start drawing this carbon, then draw the thing attached to it, then draw the thing attached to it, draw the thing attached to it, and see how we're going out every single time. You do it atom by atom and atom, okay? So that's one way to draw it using that line drawing, okay? So you start from the middle, from where your mirror is, and work your way out and put everything exactly the way you see it in that mirror. Now, if you were to take this compound now and rotate it 180 degrees, you'll end up with this, because this is forward right now, and when we rotate it around, it'll turn in the back. Notice this rotates around to this side. So this is just this image turned 180 degrees. Okay, so this would be the other representation of that sound. Okay. Switching Wi-Fi channels too, just to see if I can clear some other stuff up. Okay, so this works really well, but now that we know that we have 2 different compounds, we have to have, in our nomenclature, we always have an unambiguous naming system. So we have to be able to tell the difference between this spatial isomer and this spatial isomer. So we have what we call the Rns method. So the Rns method says that one of the isomers will always be R, and its mirror image that's non-superimposable will always be the S, okay? Which one is which is what we need to figure out now, okay? So this system will differentiate between this. And notice that even though this is a complex molecule here, if we draw our mirror here, and we look for our stereo center, which happens to be this carbon on here and this carbon on here, all we have to do is make sure our functional groups are where they are in our mirror image. So hydrogen, hydrogen, carbon, carbon, methyl, methyl, hydrogen, hydrogen, and then this big fluffy thing is back here, okay? So even though it looks complicated, follow the method of going from mirror out, and it'll make it easier for you to keep track of all the different bonds and all the different angles and wedges, like solid wedge here and dashed wedge here. Okay, so in the Rns system, we have to assign priority to the 4 groups attached to the stereo center, okay? And so what was great to do is to, once we assign them 1 through 4, 1 being the highest and 4 being the lowest, is we put 4 behind it, and then we look for whether or not the 1, 2, and 3 go in a clockwise or a counterclockwise position. My favorite way to do this is to always put 4 at my wrist. Because if you look at your hand like this, you'll have 1, 2, 3, or 1, 2, 3. And then you'll be able to assign clockwise and counterclockwise by just looking at your hand. And you can take your hand anywhere, even on camping trips, so that you can do RNS while you're camping with your friends. Anyway, so always put your lowest priority where your wrist is and look at your finger, okay? So in Latin, R stands for rectus, which means straight or correct. It also stands for clockwise. So if you have your things in 1, 2, and 3, that's going in a clockwise direction. Anytime you have priority 1, priority 2, priority 3 going in a clockwise direction, it's an R configuration, okay? Now, let's say we have 1 and 2 and 3, so now we're going in a counterclockwise direction. That counterclockwise direction is called sinister or left-handed, and therefore it's counterclockwise. Yeah, they're a little judgy on the names there, but it's the standard way at which we do things. So think R is clockwise, S is counterclockwise, and we need to figure out what priorities we have for 1, 2, and 3 on our fingers, such that we have number 4 always on our wrist. Okay, so let's talk about how to assign priority. Okay, we're going to assign priority in the exact same method we used for E and Z in the alkenes, okay? So E and Z in alkenes were defined by the atomic number, not the atomic mass, the atomic number. So hydrogen is usually our lowest priority at number 4 because it only has an atomic number of 1, okay? And so we assign all the other groups that way. So if we had a carbon, an oxygen, and a bromine, bromine is the highest number, oxygen is higher than carbon, and then carbon next. And so we would assign them in exactly the same way we do that. And if you need to remember, the nomenclature review has that prioritization based on a highest atomic number as well. Okay, so let's assume we remember how to do that from our chapter 4, and let's start assigning R and S to these systems. Okay, so if we look at this molecule here, okay, we have a chlorine, we have a carbon, and we have a carbon. Okay, so in our first pass, we have 2 things that are equal. Okay, so we have our 1 here and 1 here. And since chlorine's the highest, we're going to give it priority 1. This one has a carbon and this one has a carbon. But this one has 3 hydrogens on it, and this one has 1 carbon and 2 hydrogens on it. So that gives this the higher priority because it has the next bond over has the highest atomic number. So we're going to call that number 2, and this is number 3. Now, the way it's drawn here, we can look at our finger and say, oh, our hydrogen's back here, our chlorine is up here, our number 2 is here, and our number 3 is here. So we have 1, 2, 3, and that is going, in my mind, counterclockwise. Okay. If it's going counterclockwise, that makes it sinister or assigned as S. Okay. So we can do that for other compounds. We can even do it for cyclic compounds. And if we look at this one right here, it's drawn with the hydrogen back, so that makes it easy. We have our oxygen is a greater atomic number than carbon. We have a carbon here and a carbon here, but this carbon is only attached to 1 carbon, and this is attached to 2 carbons by our priority because we have 2 bonds to carbon there, which makes this our number 2 priority and this our number 3 priority. So again, if we range our fingers like this and we have our hydrogen back, now it looks like the oxygen would be here, so that'd be 1. The carbon number with the 2 carbons on it is number 2, and the other carbon would be here, 3. 1, 2, 3, 1, 2, 3. That is clockwise, and therefore it should be R, or rectus for clockwise. Okay? Do we see where we're going with this? Okay. That prioritization is exactly the same as E and Z, so we get to use that same prioritization on all of our nomenclature, which is great. And then we just have to figure out whether it's R or S, clockwise or counterclockwise, with our lowest priority away from us. Excuse me. There we go. And like I said before, we can have a very complex molecule here, but again, all we have to do is know what's attached to our chiral center or our stereo center. So in this case here, our stereo center is this one right here. So all we have to know is how many things are bonded to this carbon here. And so this carbon has a carbon plus 3 carbons. This carbon has 3 hydrogens. And this carbon has 3 oxygens because there's a double bond to oxygen here and a single bond to oxygen there. And oxygen ranks higher than carbon because of its atomic number. So we have 1, 2, and 3. And again, oh, you can use either hand, by the way, your right hand or your left hand. So we're going to put hydrogen back here. This is a methyl group up here. The carboxylic acid is here, and then the benzene ring is here. So we have 1, 2, 3, 1, 2, 3, and that looks like clockwise to me. So that's going to be R, and that's going to be our R-based enantiomer. Now, if we look at the mirror image, if it's non-superposable, will always be the opposite, okay? So let's go ahead and look at those, knowing that the same assignments are there. Let's go ahead and put our hydrogen back here. We have the methyl group would be closest to this finger here, then the benzene ring, then the carboxylic acid. So that makes 1, 2, 3, and that's counterclockwise, and that is S. Okay, so whenever you have a pair, one's always going to be R, one's always going to be S. Okay, questions on that? I find this hand thing works for about 85% of the people, and then with a little bit of practice. In fact, we'll be doing that during our activity on Wednesday. Okay, so again, an enantiomer is only 2 compounds, okay? It's a pair. It's a mirror image, non-superimposable pair. However, if you have more than one stereocenter, that means you have what are called diastereomers, okay? Now, I said more than one, okay? So as long as you have 1, 2 or more, that entire class is called diastereomers. However, when you have that, our number of stereocenters is the number 2 to the power of the number of stereocenters. Tells us how many possible isomers. So for one stereocenter, 2 to the 1 is 2. If we take 2 to the 2, that's 4. And if we take 2 to the 3, That's 2 times 2 times 2, which is 8. So by the time we get to 3 stereocenters, we have 8 possible isomers available to us. Okay, so it gets very complicated after 2. So if we have 2 stereocenters in a compound, we expect to see a total of 4 molecules to make up that set of diastereomers. And within that set of diastereomers, 2 of them are going to be pairs of enantiomers, 2 of them are going to be the other pair of enantiomers, unless there's a mirror image in there somewhere. All right, so let's show how we would draw these things. Okay, so the easiest way, to look at this is to draw a different kind of projection, and we call these, makes it easier, is that we draw all of the major components up and down in a straight line, and then we take our mirror and put it in the middle and then draw it out. So notice that this is one of our stereocenters and this is the other stereocenter, okay? And we have them set in space. And we go ahead and notice that we just, if we do the mirror image thing, they're going to be easy to match, easy to draw, because you're just going to work from the inside out. And then we get our pair of enantiomers for this. However, it's not the only other isomer, okay? So in this case here, one's going to be like RR and the other configuration is going to be SS because the mirror image changes that. However, we could also have a different set where one is R and one is S, and then that makes the R and the S flip on the other one. So if this was R, if this was R and this was S, this is going to be S and this is going to be R, because the mirror image is going to flip that stereo center. Okay. All right, now, so if this is a pair of enantiomers right here, because the chiral centers completely swap, and this is a pair of enantiomers here, this is a set of diastereomers, okay? So that's 4 possible isomers available to us in diastereomers with 2 chiral centers. And so we need a total of 4 compounds, okay? But that's not really the rule. When you have 2 chiral centers, you actually have 3 or 4 compounds, okay? And that's because, remember, we have to have a non-superimposable mirror image. Once you get where you have 2 stereocenters, now the mirror image can actually be rotated around a different way and overlap. And these are what we call meso compounds. Okay. So a meso compound is typically something that has at least 2 or more stereocenters. Okay. There is a pair of enantiomers, but the other pair actually has a mirror plane in them, and therefore it is a superimposable system. So let's go back to this. Let's start with this compound tartaric acid here. And notice how the carboxylic acids are matching here, and these OHs are close to each other, and these are pointing out. Okay, so that's one of the different isomers. So to make the other isomer here, all we've done is switched the OH and the H on this side to make this one here. Once we make that, if we draw that mirror image on it, what we'll see is, because we can actually put a mirror plane in the middle of this molecule, notice these match, and now the carboxylic acids match. That means it's going to be superimposable. Okay, it is still an isomer. It still has 2 chiral centers. But now, because it has that mirror plane, it is now superimposable, and therefore we have what we call a meso compound. And technically, it's an achiral compound generated from 2 chiral centers. So that mirror image within the molecule really, really you have to pay attention to that. because that'll tell us. We still have a pair of enantiomers, but then we only have one for a total of 3 diastereomers. Okay, so let's talk about planes of symmetry, near planes and planes of symmetry, so that we can see where they can show up in a bunch of different places. Okay, so in the case of near planes, they can cut through the molecule, they can cut through atoms, they can cut just through bonds. Okay, but when you do it, it means that both sides of the molecule will appear on both sides of that near plane. So let's draw attention to this one right here. So this is propanol, okay? And we know that when we looked at it, butanol has stereoisomers, but propanol didn't. Let's look at it again using a mirror plane. So in this case here, we have our hydrogen in the back here, our oxygen and OH here, okay? And if we cut a mirror between all 4 of those atoms right there, we have the methyl group above and the methyl group below, and half an oxygen, half a carbon, half a hydrogen, and half a hydrogen. It looks exactly the same on both sides. So that means that that is a near plane, a plane of symmetry, where it's the same on both the top and the bottom. All right, let's look at that again in a stick drawing here. So the oxygen and the hydrogen of the alcohol are being cut by that plane. This hydrogen and this carbon are being cut by that plane, and we have exactly the same thing on both sides of it. Okay. That's what a plane of symmetry is. Okay. Again, it can cut through atoms, it can cut through bonds, it can cut through rings. Let's look at another example of that. Okay. No, actually, we're going to move on to ring structures here. Okay, so just like we showed before, you can have ring structures that have chirality. And if you can have chiral centers in a ring structure, you can also have diastereomers in a ring structure. Okay. However, once we have ring structures, now we have to really start worrying about near planes, because when you have these ring structures, it's very easy to cut through the middle of a ring and generate a near plane. So let's look at this pair here. So let's say we just started with this compound here. We drew our mirror, and then we drew the mirror image of it. So methyl group with a solid wedge, methyl group with a solid wedge, oxygen with a solid wedge, oxygen with a solid wedge. And then the rest of the ring mirrored on that. So now, just by following that simple rule of working from the mirror out, we have now generated our pair of enantiomers. Okay. Now, if we were to take this and rotate it this direction, 180 degrees in that direction, now the methyl group would overlap with the oxygen would overlap with the methyl group, and therefore they're non-superimposable. Okay. If we flipped it this way, if we flipped it along this axis, spun it around that way, then the oxygen will be in the back and the methyl group in the back, so they're non-superimposable. Okay, so that means that if that's the pair that makes this enantiomer, let's go ahead and draw the other pair. Typically, to start the other pair, if you have them both one way or both the other way, you would try to swap one of the bonds to make your other diastereomer. Notice here, we've only swapped where this OH is. It's now, instead of being forward, it's now back with the dashed wedge. And we have this solid wedge here. Okay, so if we make our plane here, now we have a dashed wedge OH, a solid wedge methyl group, and then the rest of the ring here. Okay. So, and we found that these are actually non-superimposable. You can rotate it in your head this way. The oxygen would be out, the methyl group would be back. And rotated it around this way, the oxygen would overlap with the methyl. Sorry. Would overlap with that methyl group. So that means that we get, just like before, we have 2 stereocenters and we have 4 possible enantiomers. Excuse me. Mold must be high. Okay, so let's do that same thing, but with cyclopentadiol. Excuse me. Mute for. Sorry, I've been talking all morning apparently. So let's look at it again for this pentadiol. So it's just like the cyclohexanol, but we have one smaller bit of ring, and now what we've introduced to ourselves is the idea that we now have a Meso Center. Okay, so if we had our original compound here and made our mirror image here, and we rotated it around, you would see it would completely overlap because we have the same group on both sides. So if we rotated this around 180 degrees, the OH would overlap with the OH. And this is because cutting through this carbon and cutting through this bond, we've created a plane of symmetry. Okay, so what that means is that we actually only have one compound here. We have a meso compound for this pair of the diastereomer. But when we look at here, if we try to do that same mirror plane, the OH is on the outside, the OH is on the inside on this side, so they aren't. And if we rotated this around, we would have the solid wedge out and the dashed wedge in. So these are truly a pair of diastereomers, a set of diastereomers, and these are true enantiomers because they are non-superimposable mirror image of each other. So in this case, instead of having the 4 that we had in the cyclohexane version of this, we have only 3 because we have that plane of symmetry. Okay, so these planes of symmetry can happen a lot, especially in cyclic compounds. And they, again, can cut through bonds, they can cut through atoms. So when we start looking at things like this, especially things that are symmetrically substituted, see how there's one on this side and one on this side, and so they're 1-4 apart. When we see this, and they're the same, pointing in the same direction here, the hydrogens above and below the plane will match because they're spinning. The oxygen above and below the plane will match, and this entire bridge above and below. Therefore, because we're cutting through there, we actually have a plane of symmetry. Okay? Now, that means that the cis isomer is achiral because they're both on the same side of the ring, but the trans isomer is also achiral because, again, we've cut through it with a plane of symmetry. So now we have two compounds right here, but we don't have those planes of symmetry. We have 2 compounds. Each of them has 2 chiral centers. But because of that plane of symmetry, it wipes out the chirality. And both of these molecules are unique, however, not chiral. So it's especially prone in diastereomers with like similar functional groups, like those ones with the oxygens on it we saw, and in rings. Okay, so let's see if we can find some planes of symmetry in this system here. Now we have different groups here, so that means we're not going to find a plane of symmetry cutting through the molecule this way, okay? Because we have different groups there, we know that that's not going to happen. So let's look at planes of symmetry here. So we have methyl out, methyl with a solid wedge, oxygen with a solid wedge, oxygen with a solid wedge. And if we rotate it around this way, it won't overlap. And if we flip it over this way, it won't overlap. So we now know that we have this pair of diastereomers. Now, to get to the other, this pair of enantiomers, to get to the other pair to look at, all we do is we flip one of the chiral centers. Notice we only flip this chiral center to the other one, and then we do our same thing where we draw our mirror plane, and then we look for the overlap. Now, because the methyl group and hydroxide are different, you can't just rotate it around. They will not overlap, and you cannot rotate them around this way because they'll go in opposite directions. Therefore, we also have another pair of enantiomers. And the set of 4 are our set of diastereomers. Okay. 2. Okay, great. Lots of. All right. So that gives us, this is the exact same one we just, oh, no, I didn't. Okay. So we see that also in the cyclohexane. Again, because we have different groups right here, it eliminates our ability to do a rotation and overlap. Okay. So that gives us our pairs of enantiomers and our set of diastereomers. There we go. Okay. Okay. So just by moving one of those hydroxides, we were able to take away a plane of symmetry. I mean, we were able to add a plane of symmetry by cutting through 2 carbon atoms. We can actually find a plane of symmetry where oxygen wedge out, and then all of these carbons are in the exact same location. So that particular version of this cyclohexane diol actually has that plane of symmetry and therefore is meso. However, if we flip one of those, take this one and flip it to the back here, we lose that plane of symmetry, because if we try to draw a plane here, this one should be in the back and this one should be in the front. Therefore, they do not have a plane of symmetry, and therefore we do have our pair of enantiomers. Okay, so let's work through this one and see what we have. First thing we want to do is we want to figure out how many stereocenters we have. The next thing we want to do is how many stereoisomers are possible, and then assign R or S to all of them. And let's go ahead and look at this compound here. So the first thing we do, we want to say, is it chiral or not, is are there 4 different things bonded to that carbon? Okay, so that means this carbon right here with the 3 methyl groups is not. This has 2 hydrogens, 2 hydrogens, 2 hydrogens, 3 hydrogens, 3 hydrogens, and 2 methyl groups. So that eliminates all of those as being stereocenters. Okay. So now let's look at this one right here. Why is that a stereocenter? Okay, we have a carbon, a 1 carbon on this side. We have a carbon attached to a carbon here, so 2 carbons over here. We have a carbon attached to 2 carbons over here, but then also attached to an OH, and this is attached to a carbon. So notice we had to go 3 bonds out to see that one was different than the other. Okay. Notice we're using that same method of 3 bonds out to assign our priority as well. Okay. So that makes this our, there's a hydrogen back here somewhere. Okay. And so that there is our lowest priority is 4. This would make it 3. This would make it 2. And this would make it 1. This is our first priority here. So we've identified it has 4 different things, and we've identified its priority. So now we can call this R or S. Okay. So I believe when they draw it this way, the hydrogen is facing back, and it is. So if we put the hydrogen back, we have 1 where my thumb is, 2 where this one is, and 3 where that where. So we have clockwise rotation giving us our R configuration for that stereocenter. Okay. Let's do it again for the other one. So that stereocenter is R. Okay. Let's do it for this stereocenter here. Okay. So we have a carbon attached to a carbon, so we have that. And then we have a carbon attached to 1, 2, so that's 3 carbons, and then we have an oxygen, okay? So right away, just from the straight bonds out, we have 3 different priorities. Oh, don't forget, we have that hydrogen in the back here. So that's our 4th group, okay? So now let's assign priority. Oxygen is going to be 1. The 3 carbons is going to be 2. The 2 carbons is going to be 3. And the hydrogen is going to be the lowest priority at priority 4. So if we have our hydrogen in the back again, we have our OH here. We have our number 2 priority here and our number 3 priority here. And that's going in the clockwise position. So this is also R.
Professor Irving.
Yes.
So what you're drawing right here, even though we're looking at the same image, this is just you rotating it, correct?
Yeah, all I'm doing is putting the 4th priority here and showing you where I'm putting my oxygens and carbons.
Yes, sir. And that's all based off of the first one we did, correct?
Correct.
Okay.
So that's why I like the hand method, because if you always put it here, you can easily look at it. You line it up however the paper is, you assign it, and then you look at it.
Okay. Yes, sir.
Okay. So let's do that one more time. Practice makes perfect on this. So let's look at this carbon. We have, this carbon has 2 carbons on it. So this carbon has 1 carbon on it. So it only has that one. This one has these 2. And this one has a carbon, but it has a carbon and an oxygen on it. Okay. So, and of course, we have our hydrogen sticking out in the back here. Okay. So that being said, we now also have our priorities. So this is our number 1 priority because it's got the carbon plus oxygen. This is our number 2 priority because it has a carbon plus carbon plus carbon. And this is our number 3 priority because of our carbon plus carbon. And this is our 4 priority because it's hydrogen. Okay. And let's see, I'm going to use my left hand for this one to get it all in here. So being that the hydrogen is pointing back here, the carbon with the OH, which is priority 1, is here. The carbon with the 2 methyl groups is right here. The carbon with the 1 methyl group is right here. So if we're going around that, it is going around clockwise. So it is also R configuration. Okay. So the steps in identifying are, make sure that it has 4 different groups. And while you're making sure it has 4 different groups, you can assign priority. Okay. Once you've assigned priority, you transfer that to your template here and figure out whether it's clockwise R or counterclockwise S. And notice I switched hands because it made it easier to assign them based on how it was drawn. Okay. And both hands will work. It doesn't matter. You can do either one. Just make sure you line it up and assign them correctly. And then when you look at it, look for the clockwise or the counterclockwise. And let's see if we're right. Nope. Oh, that one pointed back. Okay. So this one actually is pointed back. So the hydrogen was pointing out at us. And that's not how I assigned it. So, but that tells us if we switch that position, we would have gotten it. But with the assumption that the hydrogens were back here and here, we were correct. Okay. What do you think? So let's do a few more for practice. Yeah, okay. Okay. So let's just look at this skeletal structure and prove to ourselves that where we have all the different stereocenters are really there, okay? So let's draw up this. This is cholesterol, it's a steroid, right? And it has, let's see, this one has, remember where there's, you gotta remember that hydrogen is wherever it's not stated right here. There's a hydrogen here somewhere. So this would be, this is different than that. So that makes 4 different groups. So that's definitely a stereocenter. okay? Notice double bonds are never have stereocenters because they can only ever have 3 things bonded to them. So you can eliminate that as a choice. Methyl groups tend to not have, most straight chains like this don't have chiral centers unless there's significant branching. So here we have this carbon's bonded to 2 carbons, this carbon's bonded to 3 carbons by priority, and this is only bonded to 1 carbon, so it is a chiral center. So that's a chiral center. That's a chiral center. Let's prove to ourselves that this one's a chiral center. 1, 2, 1, 2, 3, 4. And then this is only bonded to 3 and a hydrogen here. This is bonded to 2 hydrogens here. And there are no hydrogens on this one here. So I think this is going to be our highest priority one anyway. And then we have it going down from there. So that one definitely is a chiral center. Now notice in this flat configuration, we can't tell exactly where the hydrogens are. So we might have to draw in a different perspective to figure out all the different stereo things. So if we go through that analysis and do all of these, what we're going to end up with is the idea that we have a total of 1, 2, 3, 4, 5, 6, 7, 8. So that means we have 2 to the 8 possible stereoisomers. So that's 2 times 2 times 2 times 2 times 2 times 2 times 2, which ends up being 256 stereoisomers possible. But we don't have to know, we don't have to draw all of these, because guess what? Our body generates only 1 stereoisomer. And only 1 stereoisomer is used in that metabolism. So that is the great thing about biological systems, is that they are very specific about where they put their chiral centers, and only 1 chiral center tends to be generated. In fact, some of the compounds we'll see, like they can be diastereomers where you can have an R and S. However, only one of them will be biologically active, and the other one will not be biologically active or do bad things in your biological system. All right. So, in fact, most of the steroids like this have, between 6 and 20 stereocenters available to them, but only 1 is going to be metabolically active in the body. Okay. So now that we have chirality and we have an Rns method for determining this thing, how do we know it exists? Okay, just like when we looked at IR, we said IR vibrates with certain bonds and energy is absorbed, and so that's why they absorb in certain bands and we can see them. How do we know chirality exists? Well, chirality exists because it has a thing called optical activity. Okay, so let me describe optical activity here. Okay, ordinary light is, this wave, and it's got a magnetic moment, an electric moment, right? Okay, so it's going around like this, okay? So, but in ordinary light, we have them going in all different directions. So you can go in 360 degrees. These waves can be going in any direction they want, okay? So if we take that light where they're all going in different ways and we put it through a filter such that only the light going in this direction can pass through the filter. And so you have all these little passes, and everything going this way is blocked by that filter. So that means every wave coming through that filter is all coming in the same way. So they're polarized in lines together. They're all going the same way. So we can generate plain polarized light, or light that has only these planes. And when we do that, we can do something really special with chiral materials. When we put the chiral materials in solution and we look at the plain polarized light as it's coming through here, if that compound rotates the light from, remember they're all in this direction here, if it rotates the light, it's going to rotate all of it. And at the end of that path of your sample, you can actually tell that it's rotated either left or right. positively or negatively, okay? And if it does that, that means that compound is optically active, and that compound has at least one chiral center, okay? So let's talk about how we actually measure this thing here. So in most cases, we have what we call a sodium D lamp, or just a light that puts out a lot of light in all different directions, and then it's shot into our filter. Once we hit our filter here, only the ones that are going in the same direction will go through the filter. And so we know that it's going in exactly this direction. As the light passes through, because there's an electronic and a magnetic component to light, it interacts with the mass or the matter inside the sample, and it interacts with it in a certain way. Because it's chiral, that means it's fixed in a certain place in space. And because it's fixed in a certain place in space, it'll actually interact with it in one way and one way only. And this causes the light to start to rotate. The difference in which it rotates is what we call our optical activity, A. Okay. So, but there's a few other parameters associated with it. So when we get this, we want to say that, okay, it rotated light one way or the other. Okay. So in the case of rotating the light clockwise, we call that dextrorotatory. So it's rotating the plane clockwise. So we started up and down, and it's rotated, in your view, clockwise this way, such that we know it's gone in what we call a positive direction. It's gone in the dextrorotatory position. If it goes counterclockwise, then what it's doing is it's taking it and going negative. Okay. So then what we can do here to make sure that we have a standard way to measure sample to sample to sample, we have what we call specific rotation, meaning we take it a special way. We take the light we're using. In this case, we show it as a D here. This is the sodium metal D lamp, okay? It's taken at a specific temperature, okay? Because changing the temperature can actually change the rotation. So we have the temperature listed here. And then we take it where we have the exact same concentration used every time. Because you want the same concentration, because if you had more of it, it's going to rotate the light more. Less of it, it's going to rotate the light less. So we set a standard procedure of 1 gram per 100 milliliters, and we set the standard distance of the 10 centimeter long tube. What this means is that you're going to be interacting with the same mass of molecules going through this path every single time, and that gives us a specific rotation for that specific compound. Okay. Now, in this case here, we show that the S is dextrorotatory, and we say the R is lavorotatory. There is no way to know whether your R or S is going to tilt it one way or the other until you measure it. Okay. You can have an R with a negative rotation. You can have an S with a negative rotation. It doesn't matter. Okay. So you need to identify your RNS by your RNS rules and measure to figure out whether it's plus or minus. Okay. Now, you can even find some inorganic salts that have chirality, but there are really, really a lot of these things. And when we have them, we rarely have the opposite form exist. For example, in your biology class, you might know that a lot of these things are called L something, L sugar, or D sugar. That's actually, the L stands for lavorotatory, or the D stands for dextrorotatory. And those sugars that have those L and D, your body actually only processes mostly one kind or the other, but not both. So we'll actually see that the L and the D appear in biological descriptions of sugars, etc., and proteins because of this same nomenclature of the dextrorotatory for clockwise rotation and lavorotatory for counterclockwise rotation. Okay. So one of the things we want to talk about also is the ability of enzymes, specifically within cells, to choose one and one only stereocenter. Okay. So this particular enzyme, cretomycin, is used to help digest proteins. It's really big. Okay. It has 251 stereocenters. Okay. That means there's millions of possible derivatives of this, of stereoisomers of this. However, only one stereoisomer is ever produced by your body, meaning that one stereoisomer of those possible 251 centers is specifically built center by center by center by center by center by the different parts of the enzymes or mitochondria that make these, and so that they fit in a certain way. And guess what? Those certain enzymes have pockets that fit other molecules in certain ways, and they only react in that certain way. Okay, so these are very specific, highly chiral systems that allow us to do very specific, highly chiral work. Okay. And one of the ways that this works is because enzyme surfaces have pockets, not necessarily pockets per se, but so they'll have sections on them where they would be hydrophilic or hydrophobic or attract sulfur or attract oxygen, or only fit a certain size group inside. And so, for example, on this side here, we have a particular isomer that has an aldehyde on this side and a hydroxide on this side, okay? So the aldehyde actually has that carbonyl compound, and so it has a dipole moment. And so it has a specific pocket that dipole moment of that aldehyde will fit into, and then the hydrogen will fit into another pocket, and this will hydrogen bond to another. However, if you use the opposite isomer of that, once you line up the other two groups here, we now have something without a carbonyl. And if it doesn't have a carbonyl, it won't fit into that enzyme. And if it won't fit into the enzyme, it will not work. So it can't bind and it can't go to the next step of that biological system. Okay. All right. So this happens in a lot of the drugs we use today. Ibuprofen is a very good example of that. And naproxen, they are both NSAIDs or non-steroidal and anti-inflammatories. And both of them only work in the S isomer. The R enantiomer of both of these are inactive. Now notice they're kind of similar in structure here. We have the carboxylic acid group here that's the same on both. And it's just the ring system on this end that's different from that. So they are both using that carboxylic acid end, and it has to be that specific enantiomer to be able to be used as an active pain reliever. Now, if it's the other one, it actually looks really bad because it acts as a liver toxin. Your liver just can't process it, and it's a problem. All right. Okay, so what if you have a mixture of an RNS? We know that we have a mixture of RNS because we would have 0 optical activity. So the R is going to try to rotate it this way, the S is going to rotate it this way, and they're going to cancel each other out. Okay, so you can have like this chemical mixture of ibuprofen, and you can have it, you look at the optical activity, if it's 0, you know you have to purify it because the R is going to be the one that gives you, it is inactive, and the S is the one that's going to give you the pain relief. Oh gosh. Mold's high today, sorry. Okay, so then we can do what we call resolution. We can actually separate this racemic mixtures, or I'm sorry, a racemic mixture is one where you have equal moles of R and S. When you have that racemic mixture, you have optical activity of 0. You can separate them into their enantiomers, and you can show that you've separated enantiomers by then measuring their optical activity. Okay. So the fastest way, or the most selective way to do this, is what we call enzyme resolving agents. So enzymes, as we saw before, things will only fit in the pocket a certain way. Okay. So in the case of naproxen, they actually purify it by taking that carboxylic acid and derivatizing it to make it into an ester. And then they hit it with an enzyme, an esterase enzyme, which is one that clips off esters. Okay. This enzyme, it will only fit the S form of this ester. It doesn't fit the R form of the ester, meaning that only the S is going to be clipped to the carboxylic acid. Once you get it to the carboxylic acid, you can now separate them by just using a little base and pulling this into the aqueous phase, and this does not have a hydrogen bonding group on it, and so it won't be pulled into the water. And you can separate them by that method. Okay. So, yeah. All right, so what we're gonna do on Wednesday is I'm going to go over the priority method again. We're going to go through several examples of RNS, and we're going to try several examples of that, and then we're going to break out into our student activity, our group activity, which happens to be assigning chirality and drawing chiral compounds, and then we can upload those. Okay, so this is chirality, and I think it's best to have it all in one place. The most important thing is to be able to identify RNS and identify diastereomers and enantiomers. Okay, those are the things we're going to be most responsible for as we move forward. All right, questions on chirality, diastereomers, or enantiomers? How to know one's the other? Well, we're coming up on 150, so if you don't have any more questions, I'm going to go ahead and stop sharing and stop recording, and you can ask questions off camera.